So power series. And of course, the reason that we're interested in power series is the following result, that basically being analytic will be equivalent to having a power series representation at every point. So if you're analytic, at every point you're going to have a power series representation that is valid in some disk centered at that point. At every point you have a disk in which a power series representation is valid. Okay, and then that's actually usually what one uses to mean, that's usually what analytic means. Analytic means that the power series, at every point you have a local power series representation. And one uses the term holomorphic to mean differentiable. And so what the result is usually described that holomorphic functions are analytic functions. But because they're equivalent, we're using the term analytic to mean holomorphic in this class.
So if you go in the world, we shouldn't say analytic?
No, it's perfectly fine to, because people use these terms because it's equivalent in complex analysis. In complex analysis, you say the same thing. People use these terms interchangeably. But if you say a real analytic function, it doesn't mean a differentiable function. It means something that has a local power series representation. Okay, so just a basic definition, right? Any series of the form summation a sub n z to the n, where the n from 0 to infinity, where the a sub n are all complex numbers, and z is a complex variable. Z is a complex variable. Any series of this form is called power series. A power series centered at 0. Right? More generally, if you have something like this, a sub n z minus z naught to the n, and from 0 to infinity again, it's called a power series centered at z naught. Okay, so what's a power series? It's something. It's basically an infinite, a function that's described as an infinite series. Where the infinite series is like a polynomial. The simplest, the prototypical power series is the geometric series, summation z to the n from 0 to infinity, right? If you observe that you take the sum of z to the n, observe that if you take the nth partial sum, the sum through from n equals 0 to capital N minus 1, I'm sure you've seen this trick before. You can determine the sum, right? It turns out to be 1 plus z to the n over 1 minus z. One sees that the series converges if the absolute value of z is less than 1. Okay. Because the partial sum series, partial sum sequence is going to converge to 1 over 1 minus c if the absolute value of z is less than 1, right? And diverges if z is greater than or equal to 1 in modulus. Okay. And the reason for that is the divergence test, right? You know that the nth term, the nth term doesn't converge to 0 if your modulus is greater than or equal to 1. Okay, so this is the typical power series, and what you notice about it is that, well, there's a disk around 0, right? There's a disk around 0, and it has a certain radius, right? And inside that disk, the series converges, and outside the closure of that disk, the thing diverges. Right, and that's true of this one particular power series, but in fact that turns out to be true for all power series. That you're always going to have, whenever you have a power series, you're always going to have a disk. You're always going to have some radius, such that inside the open disk of that radius you have convergence, and outside the closed disk, then you have divergence. Okay, so that's the common behavior. Okay, so it'll be true. So this sort of behavior will be true for all power series. Okay, to see that, we're going to need a couple of. So we'll need a couple of important concepts: lim sup, lim e. Okay, the limit superior. So, I'm going to cheat a little bit on this. Let me give you the definition first. So, let S sub n be a sequence of real numbers. And let E be the collection of x which are in the extended reals. Okay, so x can be a real number, could also be positive infinity or negative infinity. Okay. Such that S and K converges to x for some subsequence. S and K. Okay. So this is the collection of all limits of subsequences of your sequence. Okay. So it's not the collection, it's not the limit of your sequence, but it's if you consider all subsequences of your sequence, and you say, what are the limits of all those subsequences? And that collection of limits is this set U. Okay. Okay. So we define the lim sup, the limit superior of the sequence Sn as lim sup of S of n of this infinity is the supremum of E. So the least upper bound of the set of this set. Okay. So just to remind right, so so for example, sort of a dumb example, if my S of n were something like -1 to the n, right, then your elements are flipping back and forth from -1 to 1, right, and the set E is going to be, what's the set E going to be? What kind of subsequences? What kind of limit points can you get from subsequences of this sequence? You've got -1, 1, -1, -1, 1, right? What? 1 and -1, right? So that's going to be E, and your lim sup is going to be 1, and your lim if is going to be -1. Okay. So there's no limit. This sequence doesn't have a limit, but it has a lim sup and has a limit. Yes.
Right. Is Just going back to defining E,
Yeah.
you extended it to include positive and negative infinity to include limit divergence?
Yeah, that's right. That's right. So you can, it's okay. So for example, if I threw in other numbers, like suppose I have 2, 3, 4, 5, and sort of scattered among my numbers, I've got n, right? Okay. In that case, my limb soup, I could have a sequence. I have a subsequence that converges to infinity, and so my E is going to contain infinity, and my limb soup would be infinity. Make sense?
Yeah.
Yeah. Okay. Right. So, okay. So one always has a limb soup and a limb inf, although you don't always have a limit. Given any set, you're guaranteed to have a limb soup and a limit. Given any sequence. Okay. Okay. Right. So yeah, just to remind people, has everyone seen this term soup? The supremum? Michael, have you seen this term? No, you haven't. That's okay. I'll quickly define it. The next thing that I'm going to say basically will allow us to avoid talking about it. But let me just define it. Let me define it anyway for your education. So, right. So if you have a set, so E be a set of real numbers. E be a set of real numbers, and then if there exists a number n such that n is bigger than p for all points in E, and we call an upper bound. Okay, so it's just anything that's bigger than everything in E, right? And then the supremum of E. So if m naught is an upper bound of E, such that n is less than or equal to m naught is less than or equal to n for all upper bounds n of E. So if you have an upper bound that's less than or equal to all other upper bounds, one calls it the least upper bound. Of E. So it's or the supremum of E. So it's denoted least upper bound of E or supremum. Okay, and basically the defining characteristic of the real numbers is that whenever you have an upper bound, there exists a least upper bound. There exists a real least upper bound. Okay, so that's like the almost the defining property of the real numbers. In the rational numbers, you can have an upper bound, but there will be no number that is a least upper bound. Say, that's possible, right? But in the real numbers, if you have an upper bound, you're guaranteed to have there's a real number that is the least upper bound. Anyway, don't worry too much. So there's these, and one has conversely lower bounds and greatest lower bounds, which are called infimums. Okay. Okay. But so the limb soup is the supremum the least upper bound of the set of limits of subsequences of your original sequence. Okay. But what we're going to use for the most part will be the following characterization of the limb soup. Okay, so the limb soup, so useful characterization. Limb soup. The limb soup is the unique number S star such that when S star is one of those points in E, and 2, given any epsilon greater than 0, there exists a limit such that n greater than or equal to n implies S of n is less than S star plus E. Okay, so this is S star. You're guaranteed that well, one S star is an E, so there's going to be some subsequence. It's a unique number for which there's a subsequence that converges to this number, and further, given any epsilon, there's a time past which you're always lower than that epsilon. Okay. Yeah.
So Sn is so least upper bound limb soup is only applies to one particular sequence necessarily. I mean, it doesn't bound all of the sequences in E necessarily. Or
Say it one more time.
does the supremum of E, is that a bound for all of the sequences or just one in particular?
It's the least upper bound of the limits of these sequences. It's not a bound for the sequence.
All right, sorry, including all of the limits. That's to apply all of the limits?
Yes, that's right.
Okay.
That's right. Yeah. So it's the least upper bound of the limits of all subsequences. So in any case, this is the useful characterization. Given any epsilon, the limb soup has this property that if you take any number that's slightly bigger than the limb soup, then past some point, everybody's going to be less than that. Okay, so it's sort of like half of the definition of a limit, right? Like if we said something like, if we said this, then that would be the definition of limit. But we're only taking half of that. So if you had something that was both a limb soup and a limb inf simultaneously, that would mean that the limit existed, and that would be that would be it. Okay, so that will be. This description of the limb soup will be the one that we'll be using. Yes.
So is that then basically saying limb soup is the max of E, the maximum value of E?
Well, except that E is not a finite set, not necessarily a finite set. So you don't talk about the max, right? Rather, it's the but it is the max. No, I'm sorry. You're right in saying that. It is the max because it's in the set, right? So it's the maximum value. That's right. Yes. Sorry. That's right. Okay. Other questions? Okay. So now that we have this vocabulary. We can prove the following theorem of Abel, which says exactly what we were saying, that given any power series, there exists a number r, where r could be 0 and it could be infinite, such that 1, if z is less than r, right, if you're inside the open disk of radius r, the series converges absolutely. And further, for any row that's less than r, any row that's strictly less than r, convergence of the series is uniform on the disk of radius rho. So if you're looking at series that are centered at 0, there's some r in which the series converges absolutely, and further on any disk that's smaller than that, you've got uniform convergence. Okay? You don't necessarily have uniform convergence on the whole disk, but on any disk smaller, you do. Okay, so this is similar to the condition. This implies, in particular, the condition that you need for Weierstrass's to apply Weierstrass's theorem from last time. Further, if z is bigger than r, in modulus, then the terms of the series are unbounded. And thus, the series is divergent. So, this theorem of Abel basically gives states the existence of a radius, right? It states the existence of a radius inside which you have this sort of convergence, and outside of which you diverge. Okay. Further, that radius is 1 over the square root. Nope. 1 over the lim sup of the nth root of the nth root of the modulus of the nth term. Okay. This last part is due to, it's called the result of Cauchy and Hadamard. I was very sad to see last time that the recording had failed. So we lost the comment about the love and the characteristic functions. But that may be for the best. Okay, so Abel's theorem, or Abel-Weierstrass. Weierstrass is everywhere. All of this can be shown as a consequence of the root test. So let's state and prove the root test that involves the lim sup. Okay. So given a series, let's then let alpha be the supremum. Let alpha be the lim sup of the nth root of the modulus of the nth term. Then, if series converges, and if alpha is greater than 1, then the series diverges. Okay. Okay. So I said that this is that Abel's theorem is an immediate consequence of the root test, right? So let's just see that. How does Abel's theorem? Right. Well, right. If you take the power series, right? So consider the lim sup and the nth root of the modulus of the nth term of the power series. Well, what do you get? You get z lim sup cn. Right. So the root test says that as long as this is smaller than 1, you have convergence, and if this is greater than 1, you have divergence, right? As long as this is smaller than 1, right? As long as this is smaller than 1, then this converges, right? And if this is greater than 1, then you have divergence, right? In other words, inside the disk of radius 1 over lim sup, right? Inside this radius, then you have convergence, and outside the radius you have divergence. So at least part of Abel's theorem seems to follow immediately, right? Because you have absolute. You see that you have absolute convergence, right? Because if you're considering the sum of the absolute values, you're just taking the absolute value of the absolute value, right? So root test says that inside here this converges, and in fact it says that this converges. So in fact that the series converges absolutely, right? And the root test also says that if this is bigger than 1 over that thing, then the series diverges. Okay. So we have the first part. First part immediately follows from the lim sup root test. Okay. Now, why do we have? What do we have left to show? We have to show that the convergence is uniform on any smaller radius. Right? So why is that true? Why is that true? So we still need to show. Can I erase this? Can I erase this? Do you want? Are you copying this? No. So, why does this thing converge uniformly on z less than rho, strictly less than r?
Question.
Yeah.
Is it so the sequence of functions in this case is the partial sum of that sequence?
That's right.
Okay.
Yeah.
Sorry.
why does the sequence of partial sums converge uniformly? Well, we have only one trick to prove uniform convergence. What is it? The M test, right? So you know you're going to use the M test. So, so what you want to do, you want to find some bounds so that the sum of those bounds converges. So there's only one thing to do. Cn is smaller than
Right, but isn't the function that you're trying to bound the sum up from
yes.
n equals
Yes. So what do we need to do? We need to find some upper bounds such that the sum of them converges, right?
Mhm.
Such that this converges, right? But this converges. Why does this converge?
It's less than R.
Because it's less than R. Exactly. So this is R. Right? Here's rho. Rho is some. Rho is inside this disk, and so you know that this converges. This converges. So these guys converge uniformly. Yes.
And so then the reason we can't say on the border because we don't know. I guess that
We don't have
the root test doesn't really tell us anything when it's equal to 1 or when
Exactly.
mod is equal to R.
Exactly. So we don't have that. If we replace rho by R, we don't have that converges.
So what does happen at those edges?
You don't know. Actually.
Oh.
And it can vary. Like it might well be that it converges at some of the points, but it might not converge at any of the points. But you can't have it converging at all the points because that would imply imply that the radius is bigger. Yeah, there will be at least one point where the convergence fails. Okay. So you see that what we have to do is prove the root test, but that's not too hard, right? So suppose that alpha is less than 1. Suppose that alpha is less than 1, so the lim sup of this is less than 1. Okay, so right. Okay. So in particular, choose a beta such that alpha is less than beta is less than 1. Okay. So choose a beta that's less than 1 but bigger than alpha. We know that since alpha is the lim sup, we know there exists a time past which this is less than beta. Because beta is slightly bigger than alpha, and what we said, the main property that we're going to use about the lim sup is that if you have anything that's bigger than alpha, you can guarantee that you're under that, and you're bounded by that. Okay, so here's something that's a little bit bigger than alpha, and we can guarantee that past some time you're below that. Okay. But what do you see happens? What's going to happen? Who sees the end of it? Well, if that happens, John? If that happens, then you see that this is true. Right. So past a point, the absolute values of your elements are bounded by beta to the n, and so what?
And goes infinity, that goes to 0.
Yes, that's right. So, what's the point? That you're bounding this guy by the elements of a geometric series, right? You're bounding this guy. You're controlling your original series. By a geometric series where the ratio is smaller than 1, right? And so the geometric series converges, and by comparison test, that makes the smaller non-negative series converge. Okay. So since beta is less than 1, we know that summation beta of n equal to infinity converges. This, and thus a comparison. Summation is okay. Part 2. If the lim soup is greater than 1, then we know there exists a subsequence n sub k, a sub n sub k, that converges to this alpha, which is bigger than 1. Right? Because of the characterization of the lim soup, right? We know that it's a limit of some subsequence, right? But what does that tell you? That tells you that a and k is bigger than 1 for infinitely. A sub n is bigger than 1 in absolute value for infinitely many n. So the divergence by the divergence test. Yes.
Could you also use pick a beta between alpha and 1?
Beta is between.
Or for the second part, could you use a similar argument?
Yeah, sure. You'd be comparing.
If beta is less than alpha or greater.
But you're still going to ultimately be using the divergence test, because what you would be saying would be that some of the terms are bigger than those in a divergent geometric series, right? Some of the terms are bigger than those, right? Yeah. So yes, I guess so, but I guess to me it seems clearer to say that because of the size of the terms doesn't go to 0, right? Then the series has to diverge. because I think ultimately that's what you say going the other way as well. Okay. Okay. So this is good, right? You have this ultimate root test, right? This root test back in calculus 2 or when you had the root test, it was always, if this limit exists, then you can say certain things, right? But that limit need not exist. However, the lim sup always exists, and so this result always applies. Okay, so that gives you the root test gives you Abel's theorem. Okay. So I think I want to do this. Okay, so I was going to talk about the ratio test, but let me, for the line of the story, continue on from Abel's theorem, and then we'll jump back to the ratio test. The ratio test turns out to be not as satisfying as the root test, but. Okay. Oh yeah, and I should also say that we've been talking about power series centered at 0. Of course, these things still hold true for power series centered at other points, right? So you just So the disk will just be centered at that other point. Okay. So as a consequence of Abel's theorem, we have this theorem about termwise differentiation, which is actually pretty trivial. So let f of c be then 1 f is differentiable, 2 f prime is summation a minus 1. You can get the derivative of the power series by differentiating termwise. Further, the radius of convergence of f prime is the same as that of f. So if you have a series if you have a function that's defined as the power series, it's going to be differentiable, blah, blah, blah. Okay. So, why is that true? Why is that true? You just need to say one thing. You need to say one name.
Cauchy?
No. Okay, if it's not Cauchy, then we'll Weierstrass. It's got to be Weierstrass. Okay, so Weierstrass. Right. We have this theorem about convergence of analytic functions. Right. Each of the partial sums here is an analytic function. Right. It's a polynomial. It's an analytic function. Right. And what we just saw was that those things converge on any, so you have some radius of, you have some disk of convergence, and what we saw was that on any smaller disk, we have uniform convergence, right? Now, what did we need to show to get convergence of the convergence to an analytic function from Weierstrass's test? Do you remember? We needed basically that you have uniform convergence on every compact set. on every compact subset. Okay, but any compact subset of this disk is going to lie in one of these subdisks, right? Because these disks, you can expand them out, right? And they will ultimately, there'll be some uniform collection of them that, so there'll be some infinite collection of them that covers the whole disk, right? Compact set is going to lie in one of them eventually. Okay. So we can apply Weierstrass's theorem, right? So what does that say? Since these guys are analytic and convergent uniformly on every compact set, and I should say that people apparently sometimes call this almost uniform convergence. Okay, so I don't have to say converge uniformly on every compact subset. Okay. So we have almost uniform convergence of these analytic functions to this function, so this function is differentiable. And further, the derivatives of those functions, right? The derivatives of those functions are going to converge to the derivative of f, right? Which is another way of saying that this sequence of derivatives of polynomials converges to the derivative of the power series. Okay. So these two follow immediately. These two are immediately follow from Weierstrass. When I was young, I think I sort of idolized Weierstrass. When I was in college, I thought Weierstrass is such a great person.
What changed?
No, I still think he's. I mean to say that my admiration stemmed from that time.
I like Picard.
Picard, yeah,
Yeah, Picard.
also cool. Also very cool. Yeah.
What about Koshi?
Koshi, oh yeah. I mean, yeah. So yeah, there are all these amazing people. Yeah. You feel like just either shamed or honored by their existence. But, as a funny story, I once met the mathematician. I don't know if you know this name, Littlewood. Littlewood. Has anyone heard of the name Littlewood?
Hardy Littlewood?
Hardy Littlewood, yeah. So he's the second half of Hardy and Littlewood, who were the great analysts in England in the early 20th century. I once met Littlewood, but in a dream. Yeah, so that's
That's a story?
what? That's a story.
What was it like?
I don't really remember. But in college, yeah, I met Littlewood in a dream. Yeah. Hardy is the one, of course, who invited Ramanujan to Cambridge, and probably the more famous of the two. Yeah, there's sort of a joke at the time that when somebody met Littlewood, he said, "Oh, you actually exist. I thought that you were simply the pseudonym that Hardy uses to publish his lesser results." Yeah, so he wasn't as great a mathematician as Hardy, but he was still quite
Wasn't Littlewood a senior wrangler though?
Yeah, I think so.
Well, Hardy wasn't.
Is that?
I think so.
What's that?
It's, right in the British system, they have this impossible test, and like the people who score the top. I don't know.
Yeah, I think if you're the top scorer on the tripods, you're the wrangler.
Yeah, you're basically well respected if you manage to get the high score on that test. Yeah, wrangler. Yeah. Yeah. Okay. So the only right. So the only thing we really need to show is that the radius of convergence is the same as that of f. But that's easy. That's also easy. So because just apply Cauchy right. You look at the lim sup of this. Well, you get the same thing as the lim sup of this. Right. Because the nth root of n goes to 1. Right. So the radius of convergence of f prime will be the same as the radius of convergence of f. And another remark that you can make at this point is that the coefficients of the power series of functions of f are uniquely determined. Right? And coefficient has to be the nth derivative valued at 0 over n factorial. Okay. Okay. So I think I'm not going to talk about the ratio test. Instead, let's go on to something more important, which is the main result about analytic functions and power series. So Taylor's theorem. Let f be analytic in a domain. So remember, domain means open connected set. And let z naught be some point in D. Then there exists a unique, we just saw that it's going to be unique. There exists a power series, summation, a sub n, z minus z naught to the n, representing f in some neighborhood of z naught. We notice, as we just did, that the nth coefficient will be 1 over n factorial times the nth derivative evaluated at z naught. And further, that what we'll see is that the power series converges in at least the largest neighborhood of z naught contained in D. So if you're analytic on D and you're looking at a point, in fact you know that the radius will be at least up to the edge. Okay. Yes.
If f is analytic over all of D, then doesn't the power series have to converge in all of D?
Well, look at how. Suppose you have something like this.
Mm-hmm.
Right? Your power series might not. Suppose your function is not analytic here.
Mm-hmm.
Right? Suppose your function fails to be analytic right here. Then your radius cannot be greater than this.
Mm-hmm.
Right? So the power series, the radius of the power series is, at each point, at each point, you have a power series expansion that converges in some maximal disk.
Oh, but they're different power series.
Yes.
Ah, okay.
Yes. Okay. So this will be a consequence mainly of Cauchy's formula. So here we go. Suppose F is analytic. Like this. And let Z be some point in that disk. So here's Z naught. Here is say R. This is Z. You take some Z inside that disk and let rho be the distance from Z to the center. So let rho be the distance from Z to Z naught. That's smaller than R. Okay. Let case 1 denote circle. I'm sorry. So let rho 1 be bigger than rho, but smaller than R. And let K1 be the circle of radius rho 1 around Z naught. So you take something that's a little bit bigger. That's going to be K1. K1's radius is rho naught. Okay. So now observe. For zeta on K1, if we consider 1 minus zeta, 1 over zeta minus Z naught, we can rewrite this here. We can rewrite this as 1 over this minus 1. Seem to have messed up something pretty seriously, but let's go on and see if we can fix it. Okay, so we're going to use Cauchy's formula like this. So okay. So this minus C we're going to write as nothing fancy. Right. Okay. And so let's rewrite this as 1 over zeta minus c naught times 1 over 1 minus zeta minus c naught over zeta minus c naught. Okay. Right. Just algebra. For now, we right, yeah, we're good. Sorry. So, but notice that z minus z naught is z minus z naught over zeta minus z naught is in modulus smaller than 1. Right? Notice that z minus z naught over zeta minus z naught, that's rho over rho 1. Right? Rho 1 is bigger than rho, right? So this is smaller than 1. And so we can express this using the geometric series, right? And we rewrite this as z minus z naught n over zeta minus z naught. And as a consequence of the M test, that this series converges uniformly for zeta on K1. So I'll leave that as an exercise, but it's immediate. Okay, so now let's use Cauchy's formula. Do it. And Cauchy's formula, well, you have that f of z is 1 over 2 pi I integral of this f of zeta over zeta minus c over zeta. Which, using the above, we rewrite as summation n from 0 to infinity f of zeta minus z naught to the n plus 1 z minus c naught to the n dz. Okay. We just replaced the 1 over zeta minus c with this. Okay. Now, again, using the fact that f is bounded on K1, one can see that this series is still uniformly convergent. Right? Because we had a uniformly convergent series, and then we just multiply it by some bounding function. Right? So you can see that it's easy to see that the new series is still going to be uniformly convergent, and so we can pull the sum out. Right? And so you get so this is going to equal summation 1 over 2 pi I f of zeta minus c naught to the n plus 1 z minus z naught dz. Okay. Over K1. Right? let me let me pull this. This doesn't depend on zeta, so we pull it out, of course. Right. And you see what we have here. Right. What do you have? You have the nth derivative of f evaluated at z naught over n factorial. Right? Z minus c naught n summation 0 to infinity. So every function, right? So your function has a power series expansion. As long as, and you see that is valid in the largest disk in which the function is analytic, okay. Or even in the largest disk in which that function is analytic. So the expansion is valid. In the largest disk about z naught, in which f is definable as an analytic function. So, it may be that there's some singularity. If that singularity is removable, you can keep on expanding your disk. Right. So the radius is in fact the distance to the nearest non-removable singularity. So this gives you the Taylor series expansion of analytic functions, and it gives you how to get them, right? So if you're looking at the exponential function, then the Taylor series expansion for it, the power series expansion is just going to be right u to the z summation z n over n factorial, right? For the sine, you'll get summation -1 to the n plus 1 z to the 2n minus 1 over 2n minus 1 factorial, and infinity, etc. So you get all this, basically the power series expansions that you got on the real line, you'll get basically the same thing for the you get the same thing for the expansion on the complex plane because of this. So I should say that this is in some texts, and I think this is actually the way to do it. In some texts, this is how you define the exponential function and the sine function on the complex plane. Right? We did it in a sort of bizarre way. We said we're gonna assume de Moivre's formula, e to the I theta equals cosine theta plus I sine theta, right? And we're going to use that to define e to the I theta, right? That must have seemed to you at the time to be somewhat suspect, right? And if you go from this, if you do this approach and rather say I'm going to define e to the z as by using a power series that converges on the entire plane. Here it is. Here's how I'm going to do it. This is going to be my complex version of the exponential function. This is going to be my complex version of the sine function and the cosine function, etc., etc. Then de Moivre's formula is a consequence, right? E to the I theta equals cosine theta plus sine theta. Sine theta is a consequence not a definition, right? And that's far more satisfying to do things that way. If you don't mind me sort of showing you something amusing, you can also see, so in particular, what you'd see is that e to the I z1 plus z2 equals cosine z1 plus z2 plus I sine z1 plus z2. And in fact, this would be true for all complex numbers, not just real numbers. Okay. And it's also and since this equals cosine z1 plus I sine z1 times cosine z2 plus I sine z2, what you get is that cosine of this is equal to this, right? And so if you equate the real part with the real part, what does that tell you? That tells you for the complex cosine function, cosine z1 plus z2 is cosine z1 cosine z2 minus sine z1 sine z2. Right? In other words, the addition formula from trigonometry is actually a consequence of the properties of exponents. Right? Right? So if you forget the addition formula, right, you have the negative, you have the sign, you have the formula for the sign too, right? It's just the imaginary part, right? You just say, well, this is going to be cosine z1 sine z1 plus cosine z2 sine z2, right? So these sort of trigonometric facts are actually just a statement about E's properties of exponents. Okay. So rather than in the text using the trigonometric functions properties to define to show that the properties of exponents hold in the complex case. Right? It's rather the opposite is true. In case you ever forget your trigonometric functions formula.